Hi everyone, my name is Uganze Matthias Joseph and I'm working with Nursery Catherine. We are presenting a project on year first generative adversarial contrastive learning for defective tire detection with knowledge distillation. Um, to give you a brief introduction on our project, this is addressing a problem within a society. For example, many people drive cars, but some of them buy faulty tires, or their tires get faulty along the way, and they can't easily detect these defaults because some of them can be very marginal and hard to detect. For example, a tire can have residual treads, but you can't easily see it unless you have something that is helping you out. For example, a machine learning model that can easily compare the treads of your tires to the treads of normal good tires that are supposed to be manufactured by the company. So in this project, we are generally going to be using gun-based machine learning, whereby we are going to feed good tires within the cycle guns, and then they will generate synthetic bad tires using generators, and then we shall have the discriminator to distinguish between the good and bad tires, and then to have to classify them. Technical definitions. In the technical definitions, we have tire defect detection, which is a process of identifying good and bad tires, detecting defaults on tires. And then we have generative adversarial networks, which is a technique in machine learning models that employs a framework having a generator discriminator, where the generator receives good images and then supposed to create realistic but bad images and then feed them to a discriminator. So a discriminator on receiving the good and bad supposed to distinguish between the good and bad and classify them accordingly. These icogans are unsupervised image to image translation framework that enable domain adaptation without paired datasets. So this will help us to classify the data without having to pair them up. Then computer vision is a branch of artificial intelligence that uses vision like cameras to take images or to detect using in form of videos and then feed this data into a learning model. Then image processing is the process of extracting details from an image and then creating either numerical data or graphs out of that data. Then knowledge distillation. Knowledge distillation is transferring of knowledge from a large and complex model to a smaller model. Then, according to the research trends, few techniques have been brought up on this case of defective tires during manufacturing, where some of them are employing machine learning based models and others are employing deep learning based models. Among the deep learning models, we have the long X-ray image detection that is used to find faults in tires using X-ray images. So a tire is taken within the X-ray room, and then they scan it using an X-ray, and then a 2D output is printed, and then it is taken to the machine learning model. It's supposed to analyze it and detect faults within this X-ray, and then recommend on either whether it's a good tire or bad tire and what default it has. Then, so to summarize the problem statement for this project, basically many accidents on the roads are generally caused by people driving on bad tires. So in case someone has a really a bad tire, for example, the treads are wearing out, a person may not easily detect it, but a camera, for example, on a machine model can be able to take the picture of that tire and then run it through the system, and it will find that the tire is not good to be driving on. And then others will have overflated tires, which can be a problem. For example, that tire can actually burst. And then others will have very underflated tires, which can make the car to be unstable. So following this problem, we have come up with actually a solution. Looking at the problem we have had in a previous slide, I think we can talk about a proposed solution. For example, developing a machine learning model using cycle guns, or say guns, that is going to help us uh, to distinguish between the good and bad tires. And then this model will use a computer vision, for example, using cameras and so on, capturing these images on the road, or even on cars that are parking somewhere, and then it will take pictures of those tires and then run them through the algorithm, and then be able to distinguish and recommend on whether to replace those tires or to continue using them. Then you can also use it in the manufacturing actually itself, whereby the tires can be able to be manufactured with a standard that is will be long lasting and can be used for good. And then we shall have knowledge distillation. This will help us with the efficiency of the model. And then convolution on neural networks. This will help us in graphical representations and other distributions. Then regularization, this will be a technique to use in mitigating overfitting, for example, resizing the images and so on. Then on my side here, we're actually having a methodology or a representation of this project. I think you can see we're starting by acquiring the images of the tires, and then we shall do a EDA process, and then we shall go on and process the tires through data processing, and then we shall do feature extraction, cycle guns, contrastive learning, edge distillation, real-time deployment, and then evaluation. And to move on our data set. Our data set is comprising of about 1,856 high resolution images. This is having a big pixel of 3,000 times 3,000, and it was obtained from mainly dataset. So it includes good and bad images, good and defective tires, and then we shall have to convert or resize the images to something like 256 or 255 pixels, so that it can easily be worked with, like the process of computation and processing. Then we shall have to plot analytical graphs such as histograms, grade level, concurrency matrices, and so on, as we shall see in the future.
I'm going to take you through the local binary patterns and the discrete wavelength transformation. And the local binary patterns, or the LBP, captures local texture by comparing each pixel with its surrounding. Then when you look at the discrete wavelength transformation, the images are composed into the LL, which is the approximation coefficients, the LH, the vertical detail coefficients, the HL, the horizontal detail coefficients, and the HH, the diagonal detail coefficients. So when you look here in our images, you realize that we already have the originals. So the originals, we are going to use them for comparing. The LBP, the DWT, the DWT as well. So these are our images we are going to be referencing for this part. So let's go on. The LL is a low-frequency component that represents the overall smooth average structure, while the LH will show the vertical changes in the boundaries in texture. You can see from here we have the LH and we have the LL of the good tire, and here it's the good tire as well. So when you look at the HL, it will capture the horizontal changes in texture, and the HH image contains the diagonal edge details, revealing more intricate high-frequency features. So as you look at them, you realize that the HL will have the horizontal changes, and the HH of the good tire here will have the what? The diagonal changes. Yes. We are going to look at the GLCM contrast distribution and the correlation graphs, and as you can see here, we are going to say that we have our contrast distribution. When you look at the good tires, you realize that they have a much lower contrast distribution compared to the defect tires, the defective ones. What does that mean? They have similar features. Okay, when you put them together, they have similar features, but when you look at the defective ones, they have dissimilar features. They are unique. Yes. So we could look at the correlation distribution, and the correlation distribution will have the good tires having a more correlation compared to the defective ones. You could see it from here. So this means that they have more similar features, like how I said before, and the same goes for the defective tires. Since they have unique features, they will have a low correlation distribution. So now when you look at the HOG feature box and violin plot, you realize that we have the box plot. This box plot has a tail here. So this tail will signify the features that we have, and when you look at the defective tires, they have a longer tail. So this HOG feature box plot will in short look at the features and then identify which are similar. So the good tires have similar features, where the defective tires have more unique features. So when you look at the violin plot, you realize that this is our violin. So it has a high, actually this one has a small width compared to this. So this width signifies that good tires have closely related features, while the defective tires will have features that are much more unique to each other. Yes. I'm going to take you through this map, and it's a heat map generated from the GLCM contrast, correlation, and the HOG mean. So we want to look at the contrast here, and you realize that this contrast has a strong negative correlation with the GLCM correlation, which means when contrast increases, the correlation decreases. This shows that the GLCM contrast has rougher textures, and as those textures come about, that means they have more unique features. So that is contrast. Then the other one will be the opposite. So when you look at the contrast and the HOG mean, you realize that this contrast that we have here has a low positive correlation with the HOG mean, and it means they are almost independent. So the contrast does not strongly affect the HOG features. Then lastly, we shall look at the GLCM correlation with the HOG mean, and this shows that there is a negative, it's a positive, actually it's a negative correlation, and it is weak. So it shows that they are highly correlated, and they have fewer dominant edges. Yes. I will take you through the PCA, which is the principal component analysis visualization. We are going to look at this graph here, and it has red dots and green dots. So the green dots signify good tires, and the red dots signify the defective tires. So as you look at this image, you can see that they are overlapping each other. The good and the defective tires are overlapping each other, which means that our model might not be able to might not fully be able to distinguish between the two categories. Yes. So now we have the x-axis. So the x-axis it seems to capture the variance of the data, because you can see it stretches. What do they mean by it stretches? When you look at our scale here, you realize the scale is much long, and the last image we have here is in towards 4,000. Yes. So it stretches, which means they spread along PC1. Yes. While the others remain clustered with the good tires. Now when you look at the y-axis, it shows less spread, meaning that it captures less variance compared to PC1. And I told you, as you look at your scale, you can see it here. Yes. So the PCA itself, um, what are shared segmentation graphs? So what could we say about this? When you look at them, you realize that the features the number of regions keep on increasing towards the right, and the frequency will increase as you move upwards. But when you look at the one for the good tires, realize that it has a small number of segmented regions, which means it has a uniform texture, leading to a few distinct regions. Yes. So when you look at the one for the defect tires, the defective ones, you realize that it has a wider spread to the graph, and that means that the region counts are higher compared to the tires, and that is brought about by the uneven textures. I am going to take you through the k-means clustering graph, and right now we have this figure over here. Our y-axis is the GLCM correlation, and our x-axis will be the GLCM contrast. Yes, so here we have the grouping being based on the contrast and correlation, as I've talked before. So the blue cluster has a mid contrast and high correlation. So this could be the tire trends, since they seem to be similar but could differ due to worn out tire trends. When you look at the gray cluster over here, it has a low contrast by a high correlation, and this represents smoother areas of a tire. Yes, and lastly we shall have the red cluster, and this red cluster has a high contrast and a low correlation. So this probably is the defective or the extreme wear regions, where these clusters and the features are without labels can be obtained. Yes. The grab cut segmentation graphs have values ranging from 0 to 1 for both the good tires and the defective ones, and it shows that the distribution itself is almost binary, and the graphs are almost identical. The scales are a bit different, but when you look at it, it's actually almost the same, and it may not be sensitive to tire defects in our case, and that's why it may not capture the detailed texture changes. So we'll have to drop this. These are our references. Thank you.